Normal distribution is essentially the grandmother of the field of statistics. Much of the field and its associated methodologies somehow or another find a common ancestor in the normal distribution. Of course, the normal distribution would not exist without its spirit mother, which preceded it, that being the binomial distribution, but perhaps that's another conversation for another day. I've split the lectures pertaining to normal distribution between a few videos because the topic is important enough to warrant thorough discussion. Of course, we wouldn't have the normal distribution if not for Carl Friedrich Gauss. And I'm going to refer to Carl Friedrich Gauss as Gauss for the remainder of these slides. However, the Gaussian curve, also known as the normal distribution, was originally postulated by Gauss within the Holy Roman Empire, which at that time was known as the Holy Roman Empire, would later become known as Germany. But as mentioned, the foundational aspect of much of statistics is found within the Gaussian curve. It derives from the Gaussian methodology in one way or the other, and it's frequently observed throughout the natural world. In that way, it's similar to pi, the Fibonacci sequence, the golden ratio, etc. So let's talk a little bit about the history of the normal distribution. The discovery of the dwarf planet Ceres, an object which can be found within the asteroid belt, led to excitement throughout Europe. Gauss utilized past observational records of the planet to successfully create a formula to predict the planet's orbit. The successful prediction of Ceres' next appearance to astronomers won Gauss wide acclaim. The normal distribution was produced as a byproduct of Gauss's astronomical endeavors. So you have to keep in mind that this was a huge deal at the time in the Holy Roman Empire and throughout Europe because we didn't have Facebook, TikTok, or YouTube. So this won Gauss at the time what we would probably consider today to be viral fame. Now, something very important to remember about the normal distribution is not all data is normally distributed. As previously mentioned, the normal distribution is a foundational aspect of the field of statistics, and the reason for such pertains to most statistical methodologies being based on the assumption that data will somewhat conform to this distribution type. All right, so again, it's important to remember what's bolded and in caps up here with 3 exclamation points, that's how important it is, that not all data is normally distributed. Now, you may be led to believe otherwise in your Stat 101 course, but this is something to keep in mind as we proceed throughout these lectures. If you're in a course and you're working with data, if you're told that the data is normally distributed, it's normally distributed. Work from there. However, in the actual real world observations, data, etc., phenomenon, data is going to either be close enough to a normal distribution that the similar assumptions of the normal distribution are applicable, or close enough in which we can use a different sort of methodology, which assumes that the data is close enough to the normal distribution, but then leaves room for robustness. And this will make more sense as we go forward. But most important to remember, at least as it pertains to this batch of slides, this lecture, is that not all data is normally distributed. However, if you're in class and you're told that the data that you're working with is normally distributed, it's normally distributed. However, the normal distribution is sort of a textbook definition, a perfect example of something's occurrence. So this, again, restates what we just discussed. It's important that the normal distribution be conceptually understood as the concept of distribution extends beyond the limited aspects of this context. Additionally, many other methodologies of statistics require normally distributed data to be successfully utilized. Finally, other distribution types, such as the t-distribution, were structurally influenced by the normal distribution. So let's take a look at the normal distribution. So assuming that data is perfectly normally distributed, if we were to graph the probability of that data, the observations, we would come to a probability distribution plot that looks and resembles what is displayed here in this slide. So our mean would be smack dab in the center, and 68% of our observations would be within 1 standard deviation, approximately. Approximately 95% of our observations would be contained within 2 standard deviations, and approximately 99.7% of our data would be contained within 3 standard deviations of the mean. And we'll do an example of what I'm discussing in this slide prior to ending this particular lecture. So, as it relates to data falling within a certain distribution portion of a normal distribution, that is referred to as Chebyshev's theorem, aka the empirical rule, because Chebyshev was the first one to make this observation as it relates to data falling within a certain pattern on the normal distribution. And again, we should expect approximately 68% of our data to fall within 1 standard deviation of the mean, 95% of the data to be within 2 standard deviations of the mean, and 99.7% of the data observations to be within 3 standard deviations of the mean. And this applies to normal distributions only. Remember, we're operating, as far as these slides are concerned, under the assumption that all the data that we're assessing comes from a normal distribution, a perfect normal distribution. So, in this example, we'll find the mean and standard deviation of a data sample, and we will then estimate the z-score of 2 data points. So if you're working in your class and using this particular lecture to supplement the material, a z-score is synonymous with a standard deviation of a normal distribution. So if someone speaks of a z-score equal to 1, that means 1 standard deviation to the right. A z-score of 2 is 2 standard deviations to the right. A z-score of -1 is 1 standard deviation to the left. A z-score of -2 is 2 standard deviations to the left. And this will make much more sense as we proceed through this lecture. But in any event, let's assume that we've sampled some data from a phenomenon, and these are our data points, our observations of our sample. There are 10 observations, n equals 10. The mean of this sample, remember, mean, average, 47.5, and the standard deviation is 10.90. So that would mean if we were to graph our data or place our data points on the probability distribution corresponding with this data, which would be a normal distribution, we should expect to find 68% of our observations within 1 standard deviation of the mean, 95% of our observations within 2 standard deviations of the mean, and 99.7% of our observations within 3 standard deviations of the mean. So if we take a look at this number line on the bottom here, our mean is smack dab in the center. And that's where it's always going to be if our data is normally distributed. If we're drawing a probability distribution, a normal distribution for our data, and the data is normally distributed, mean is going to be smack dab in the center of the bell. All right, so smack dab in the center, 47.5. There's our mean. There it is. And as we move out 1 standard deviation, so that would be z is 1 here. That would be 47.5 plus 10.90. That would be our value here. 1 standard deviation to the right. Z equals 1, standard deviation is 1. 1 standard deviation to the left would be 47.5 with the value of 10.90 subtracted from it. So that would be z is -1. So where we would expect 38 to fall on this chart, and what would the approximate z-score be? Well, it looks like 38 is going to fall right over here somewhere. So it looks like 38 is here. So it looks like the approximate z-score for 38 is, give or take, -1. Where would 60 fall on the chart, and what would its approximate z-score be? Well, it looks like 60 is, here's our one standard deviation, z equals 1. So it looks like our value of 60 itself would be, I don't know, it probably, what is this, 10 point, our standard deviation is about 11. 60 is 11, so that would be 58.5. So it would be approximately a little bit more than z. So maybe it's z equals 1.125 or something like that. But anyway, it's going to exceed our z-score equals 1 because it's greater than one standard deviation out, not by all that much. And we'll go over this in an example before we close. So when illustrating a normal probability distribution, the mean value is always going to be smack dab in the center of the diagram, right in the middle of the bell. And after deriving the standard deviation, draw lines beneath the curve to designate a distance of 1, 2, or 3 standard deviations to the right of the mean and 1, 2, 3 standard deviations to the left of the mean. Remember, these standard deviations also equal the corresponding z-score values. All right, so this next slide is a bit of a doozy, so don't get too intimidated, all right, because there's a lot going on. Here is the data graphed out in its entirety from our earlier example, our example here. So the mean is 47.5 and the standard deviation is 10.90. So our data is normally distributed. So our probability distribution is a perfect bell. And what this really means, we'll get into in our next lecture. But in any event, we have our mean right in the center. So first we have our number line. Mean is in the center, and then like any other number line, our values are going to get smaller as we move to the left. And our values are going to get larger as we move to the right. Okay? Smaller to the left, larger to the right. And these are the values. These are our observational values. So the mean is right in the center because this is a normal distribution. As it is a normal distribution, and it is graphed as such, we would expect one standard deviation to the left to be 47.5 subtracted by the standard distribution, excuse me, the standard deviation. So 47.5 minus the standard deviation, one standard deviation, is 36.6. So that is a standard deviation of -1. We've moved one standard deviation to the left, and all we did was we took the mean value and we subtracted one standard deviation. Our standard deviation was 10.9. Our mean was 47.5. We subtracted 10.9 from 47.5, and we came to the value of 36.6. So z is -1, one standard deviation to the left. If we wanted to move two standard deviations to the left, we subtract 2 times the standard deviation from 47.5. So 47.5 minus 10.9 minus 10.9 gives us the value of 25.7. So 25.7 is our value, 2 standard deviations to the left. So z is -2. And we're 2 standard deviations to the left. Now, if we're moving to the right, 47.5 plus 10.9, that's 1 standard deviation to the right. So in that case, z is 1, standard deviation is +1, and our value is 58.4. Now, if we're moving 2 standard deviations to the right, again, it's our mean value plus 1 standard deviation plus 2 standard deviations. So in that case, standard deviations are 2. Z equals 2. So we're 2 standard deviations to the right. And with Chebyshev's theorem, or the empirical rule, in place, we would assume that we would find 68% of our observations between 36.6 and 58.4. 1 standard deviation to the left, 1 standard deviation to the right. So 68% of our observational values should fall between these two values here. 68% of our values, 68% should fall between these two. 95% of our values should fall between 25.7 and 69.3. And the reason that is we're opening the window. So 68% of our observation should fall between 36.6 and 58.4 approximately. 95 should be between 25.7 and 69.3. And then if we added another standard deviation, that is where we would expect 99.7% of our observations to fall. So in conclusion, the mean is the middle value on the standard normal distribution probability. And the standard deviation is utilized to measure the distance of values in relation to the mean. So let's wrap up with a nice example. Let me get my paint ready to go. So prepared to be blown away with my art skills here. All right. So hopefully this makes clear what I was trying to demonstrate within the slides, if the slides did not make it clear enough. So we have a set here. This is set A. All right, and set A contains the observational values of 7, 3, 7, 4, 5, 6, 6, and 5. And there are 8 observations. 1, 2, 3, 4, 5, 6, 7, 8. 8 observations, okay? What we want to do, and we're going to be told by our professor or on the worksheet or whatever it may be, that this data is normally distributed. All right, so you're told it's normally distributed. So you then can proceed with all of the assumptions related to such. All right? All right, so where do we go from here? All right, so first, let me draw my normal distribution. All right, so imagine that this is a perfect symmetrical bell. It's not going to be, but just use your imagination, all right? Getting kind of close. There we go. So where would our mean go if we were to derive it? If you said right here in the center, you are correct. So this is where we're going to place our mean. So let's use R to find our way around this curve. So let me get our R pulled up here. Here is R. And we're going to be working right within R. We're not going to be working in RCommander. So we're going to remove our objects. Okay. Here we go. So first thing we want to do is create data vector A. And data vector A is going to be our set A that contains the elements 7, 3, 7, 4, 5, 6, 6, and 5. So let's go ahead and assign those elements. So as you can see, we now have data vector A. So we're going to need the mean and the standard deviation for any of this to work out. So first we'll discern the mean. So our mean is 5.375 if you can't see it there. So we'll round that up to 5.38. So our mean equals 5.38. All right, now we need to get our standard deviation. So let's derive that. So the function for deriving a mean of a vector is mean with your vector in between the function parentheses. And for standard deviation, it's SD with your vector name in between the function parentheses. So let's get that. So our standard deviation is 1.407886. We'll round that to 1.41. And this is the Greek letter mu, the lowercase mu, and this is lowercase sigma. Those are the symbolic notations we're using here. This is standard deviation, and this is mean. All right, so let's put our mean smack dab in the center where it belongs, and it's only going to be here because our data is normally distributed, okay? Only here because our data is normally distributed, and the only reason this is a perfect symmetrical curve is our data is normally distributed. And we'll get into what this curve is actually seeking to illustrate to us in the subsequent video. So now what we need to do is we need to put some values down on our number line. So this is a number line, okay? It's going to go from, it's going to go in infinity in either direction. But we'll say that it'll eventually hit 0 before continuing on its way to infinity. And it's also going to go infinity in the other direction as well. But in this case, we're counting down, and in this case, we're counting upward. But in any case, we want to place the values, which would be 1 standard deviation to the right and 1 standard deviation to the left of our mean. And these values are only going to fall in perfect order here because our data is normally distributed. All right, so we have our mean value and we have our standard deviation. So let's add 1 standard deviation, which is 1.41. Okay, we rounded it up to our mean value. So let's go ahead and do that. So in our console here, we can see that that value is 6.79. So let's write that down. So this value here is 6.79. Okay. And then to the left, we have to subtract 1 standard deviation, 1.41, from the value of 5.38. Because again, this is our mean. We're going to subtract 1 standard deviation from it. So let's do that. So we're subtracting 1 standard deviation, and we come to the value of 3.97. So this value is 3.97. There we are. So this would be considered to be a z value of 1 because it's 1 standard deviation. And then this would be our z value of -1. Or excuse me, that would be negative z. So this is positive 1z, and this is negative 1z. And it's just corresponding with the number of standard deviations that we're moving to the right or the left. So by that logic, this value over here would be positive 2z, 2 positive standard deviations. And this value would be negative 2z, 2 standard deviations to the left. And if you have to use z values, I'm sorry, some of the purists will have you use them to determine the probability under the curve. And we'll do that later, but we'll have a computer do it for us. But there's a long process in which you'll use these tables in the back of your math or statistics textbook to help you derive probability if data is normally distributed. I might do a video on that at some point, but for the sake of having a computer do it and for the sake of just understanding what the computer is doing, when we talk of z values, we're talking about the number of standard deviations to the right if the values are positive or to the left that we're navigating within our normally distributed data. Okay, so what do you think that this value ought to be and this value ought to be? How will we find these values? Well, if you said that we're going to add 2 standard deviations to the mean for this value and subtract 2 standard deviations of the mean for this value, you are correct. So let's do that in R. So here we have our mean value. Here's our standard deviation value. We're going to add 2 standard deviations to our mean. And then down here, we're going to subtract 2 standard deviations from our mean. So that gives us a value of 8.2 and 2.56. So this value is 8.2, and this value is 2.56. So what's going on here? Why even do this? Well, we're doing this just to illustrate everything that's happening as far as the number line is concerned, all the goings on as far as normal distribution is concerned, and as a way to illustrate the empirical rule. So if the empirical rule holds, which it ought to because we're working with a normal distribution, aka Chebyshev's theorem, the empirical rule, one and the same, we should expect to find 68% of our observations, approximately 68% of our observations, between the value of 3.97 and 6.79. So 68% of our observations should fall between these two values. 95% of our observations should fall between 2.56 and 8.20. And then 99.7% of our observations should fall between a third standard deviation or 3z, negative 3z or positive 3z, depending on which direction we're going. We should expect to find 99.7% of our observations approximately between these values, whatever they may be. You can do the math if you want. It would be 3 times the standard deviation plus the mean for this value and minus 3 standard deviations from the mean for this value. But as you can see, we're just opening up the window. So 68%, 95%, 99.7%. So where do these values fall? Well, 7 is going to fall here somewhere. So we'll say 7 is here, somewhere over here. We have 2 values of 7. We have a 3, a 4, and a 5. We have a 6. We have actually 2 6s and another 5. So if we were putting the data on the graphic, that's where we would expect these values to be. All right. So that is it for our demonstration of the normal distribution. And if you've made it this far, congratulations, you've gone through one of the heavier lectures of this series, and they're going to be heavy moving forward because we've kind of already exhausted all of the foundational material. But if you did stop by, I do appreciate it, and I hope you're able to take away something from this lecture that will assist you throughout your coursework or whatever it is that brought you here to begin with. With that, hope to see you again. We'll be doing another lecture on the normal distribution in our next video. And take care. Have a wonderful rest of the night. Bye-bye.